Let's start in about 2 minutes or so, guys. Let me know if I'm not audible by any means. Just send a message or just unmute yourself and let me know if I'm not audible. I will share the lecture once we are done, the lecture note once we are done with the lecture, along with the problems and solutions of this particular lecture. So we'll start in about 2 minutes or so, giving some time for the others to join in. Okay, let's start things off. It's 3:05 now. Again, if I'm not audible, please let me know. Um, so today's lecture is lecture 7. Lecture 5 is what I did last time. Lecture 6 is only just applications of lecture 5. I'll share both lectures 6 and 7 once we are done with today's lecture. Lecture 6 is only an extension of lecture 5. So today's lecture, in today's lecture, we're going to look at matrices very specifically. What I have here shown to you on the screen is the lecture structure that we're going to follow for this particular lesson. So we are first going to look at vectors and vector operations before we come to matrices. Then we are going to look at matrices, the types and basic operations. And then we will look at systems of linear equations and matrix representation of that. Then in order to solve those um, linear equations, we will look at the inverse of a matrix and solving linear systems. The fifth area that we're going to look at is determinants and their interpretations. And then the sixth one is very short, just some applications in economics for you to just read through. So this is the lesson structure for today. So in this particular lesson, we are first going to look at vectors. What is a vector, and then the basic operations of vectors, and things like vector addition, what the dot product of a vector, the economic interpretations, a couple of examples, and key takeaways from vectors. So first, let's have a look at what vectors are. Right. So I hope you can see the screen, and I hope I'm audible. So what is a vector? That's the most basic question one can ask. So a vector is, as I mentioned here, is an ordered list of numbers. Vector is an ordered list of numbers, and you can think of a vector as a point in space, identified by coordinates. For example, so if you have an XY space like this, right? So this here could be a vector where on the x-axis it's denoted by 2. On the y-axis, let's say it's denoted by 3. That's one vector. Or it has a particular direction. And also, this can be another vector. So for example, here we have, let's say, -4. And on the x-axis, we have, let's say, -2. So this is a vector denoted by that. So this would be a vector denoted by -2, 4. This would be a vector denoted by 2, 3. The first part is the x-axis. The second part is the y-axis. So that's a vector. And so as I mentioned here, this is a general representation of a vector. It's an ordered list of numbers where you have n tuple of numbers, n numbers. So the vectors can be represented in different ways. This here is called a row vector. It's called a row vector, or you can represent it as a column vector, just a set of numbers. So what are some of the basic operations on vectors? So we have something called vector addition. Just like in real numbers, we have something called vector addition. You can add two vectors. So for example, if you have, like I've given here in generalized form, let's say a vector A is given by 1, 2, and another vector B is given by 2, 3. The addition of these two vectors is given by 1 plus 2, 2 plus 3. So you simply add the first two, which is on the x-axis, and add the next two, which is on the y-axis. So then you get A plus B vector as 3, 5, vector addition. So here, what I've given here is a more general form where I have a vector A denoted by A1, A2, A3, and another vector B given by B1, B2, B3. And then what is A plus B? It's simply you add in A1 with B1. That's what you get here. A2 with B2. That's what you get here. And finally, A3 with B3. That's what you get here. So that's vector addition. Similarly, you have something called scalar multiplication, where you're multiplying a particular vector A. So you have a vector A, say, as I've given here, A1, A2, let's say A3. And then you want it to be multiplied by a scalar K. Let's K. So what happens then? If you were to multiply a vector A by a scalar K, you would be multiplying all these numbers within the vector. That's what's going to simply happen. Ka1, Ka2, Ka3. So for example, again, if you take a vector A, let's say 5, 6, 7, and you take a scalar, let's say it's 3. So then Ka is simply 3 times 5, 6, 7, which is 3 times 15, 5 is 15, 3 times 6 is 18. You have to multiply all the numbers. 7 times 3 is 21. So now Ka is this. That's a scalar multiplication. So you can multiply a vector by a scalar, single number. And then you have, like in the real number line, something called zero vector. So the zero vector is very similar. It's a set of zeros. So for example, a zero vector is not only the number zero, it represents a series of numbers. So in this case, in this case, it could have two zeros or three zeros or four zeros, whatever it is. So let's take another vector again, A, which is 10, 1, 2. And then you have a zero vector, which is simply 0, comma 0, comma 0, right? Then the vector A, when you add in the zero vector, that is 10, comma 1, comma 2, plus 0, comma 0, comma 0. So you're adding in the separate items like this, you still get the same vector. A plus 0 is simply A. That's what I've told here. So here what I've told is when you take any vector V and you add in a vector 0, you get the same vector, very similar to real numbers again. And then you have something called a negation of a vector. Now in real numbers, let's take the real number, let's take x equals to, um, then y equals minus 2, y would be the negation of x, right? Why is that? Because x plus y, which is 2 plus minus 2, gives you 0. Similarly, in vectors, if you have a vector v, then the negation of this particular vector is minus v, such that if you add the two vectors, you should get the zero vector. Now, for example, let's take v to be 2, comma 3, comma 5, and let's take your other vector. Let's take this as v1. Then let's take v2, another vector, which is minus 2, minus 3, minus 5. So if you were to add v1 and v2, what do you get? You add the first two, 2 plus minus 2. You add the middle two, 3 plus minus 3. And then finally you add the last two, 5 plus minus 5. So you get 0, comma 0, comma 0. So what is this? This is the zero vector. Then we call v2, the vector v2, as the negation of the vector v1, right? So what did we talk about? We simply introduced what a vector is. It's a ordered list of numbers. You can represent it as a row vector, the ordered list of numbers in terms of a row, or you can represent it in a column vector, right, as a vertical list. Then we looked into some of the very basic operations on vectors, on these ordered list of numbers, which is vector addition and subtraction. If you multiply a vector by a scalar, and the zero vector, and finally this the negation of a particular vector. One thing that I missed here is another important aspect, which is we will talk about it later as well. We call this, there's something called transpose of a vector. Transpose of a vector. We will look into it later. So what is the transpose of a vector? Well, if you have a vector A, let's say 1, comma 2, comma 3, now this is a representation of a row vector. Now, if I were to transpose this, its symbol is this particular sign, what we call it as a prime. This denotes the transpose of the vector A. So how would you write that? The transpose of a vector is simply, if you have a vector in a row form, the transpose of that would be a column vector. And the same thing applies the other way around. So if you have a vector B, which is a column vector, let's take 2, 3, 5. The transpose of that vector would be 2, 3, 5. So this is a column vector. This is a row vector. Right. Now, a little bit into the illustration of what vectors are. So we talked about vector addition, but what does it look like graphically? So here I've taken an example. Um, on the right hand side of the screen, you see I've taken a vector which is 3 comma 2, and another vector b which is 1 comma 4, and the two vectors, if I were to add, I will get 4 comma 6. Now how does it look like graphically? So on my xy, or yeah, let's take xy plane, I have the a vector which is 3 comma 2. So 3 somewhere up to here, and 2, that is my a vector. And what is b? 1 comma 4. So b is 1 on the x-axis, comma 4. So somewhere like this. This would be my b vector. So a plus b is simply, what I do is I take the head of this a vector and join it with the tail of the b vector. So this is again b. I'm simply copy pasting b over here, such that when these two are joined together, this particular vector is the a plus b vector, which is what I get as 4 comma 6, right? So this particular vector is 4 comma 6. That's what I've shown in this particular graph. So we have, what I've written here is, so the blue arrow, that is your a vector, and the green arrow is your b vector, and the one in maroon, not red, maroon, is the a plus b vector. So we will look at a particular video as well for you to understand this, but bear with me for now. There is a graphical understanding of what vector addition looks like, because earlier what we did was a more numerical aspect, numerical example. So before we go into dot product, I want you all to watch this particular video, because this is by 3 blue 1 brown, and it gives you an understanding and a quick introduction to vectors. Again, if the audio is not clear, please drop a message. So let's have a look at what he says.
The fundamental, root of it all building block for linear algebra is the vector. So it's worth making sure that we're all on the same page about what exactly a vector is. You see, broadly speaking, there are three distinct but related ideas about vectors, which I'll call the physics student perspective, the computer science student perspective, and the mathematician's perspective. The physics student perspective is that vectors are arrows pointing in space. What defines a given vector is its length and the direction it's pointing. But as long as those two facts are the same, you can move it all around and it's still the same vector. Vectors that live in the flat plane are two-dimensional, and those sitting in broader space that you and I live in are three-dimensional. The computer science perspective is that vectors are ordered lists of numbers. For example, let's say you were doing some analytics about house prices, and the only features you cared about were square footage and price. You might model each house with a pair of numbers, the first indicating square footage and the second indicating price. Notice the order matters here. In the lingo, you'd be modeling houses as two-dimensional vectors, where in this context, vector is pretty much just a fancy word for list, and what makes it two-dimensional is the fact that the length of that list is 2. The mathematician, on the other hand, seeks to generalize both these views, basically saying that a vector can be anything where there's a sensible notion of adding two vectors and multiplying a vector by a number, operations that I'll talk about later on in this video. The details of this view are rather abstract, and I actually think it's healthy to ignore it until the last video of this series, favoring a more concrete setting in the interim. But the reason I bring it up here is that it hints at the fact that the ideas of vector addition and multiplication by numbers will play an important role throughout linear algebra. But before I talk about those operations, let's just settle in on a specific thought to have in mind when I say the word vector. Given the geometric focus that I'm shooting for here, whenever I introduce a new topic involving vectors, I want you to first think about an arrow, and specifically, think about that arrow inside a coordinate system, like the xy plane, with its tail sitting at the origin. This is a little bit different from the physics student perspective, where vectors can freely sit anywhere they want in space. In linear algebra, it's almost always the case that your vector will be rooted at the origin. Then, once you understand a new concept in the context of arrows in space, we'll translate it over to the list of numbers point of view, which we can do by considering the coordinates of the vector. Now, while I'm sure that many of you are already familiar with this coordinate system, it's worth walking through explicitly, since this is where all of the important back and forth happens between the two perspectives of linear algebra. Focusing our attention on two dimensions for the moment, you have a horizontal line, called the x-axis, and a vertical line, called the y-axis. The place where they intersect is called the origin, which you should think of as the center of space and the root of all vectors. After choosing an arbitrary length to represent 1, you make tick marks on each axis to represent this distance. When I want to convey the idea of 2D space as a whole, which you'll see comes up a lot in these videos, I'll extend these tick marks to make grid lines, but right now they'll actually get a little bit in the way. The coordinates of a vector is a pair of numbers that basically gives instructions for how to get from the tail of that vector at the origin to its tip. The first number tells you how far to walk along the x-axis, positive numbers indicating rightward motion, negative numbers indicating leftward motion, and the second number tells you how far to walk parallel to the y-axis after that, positive numbers indicating upward motion, and negative numbers indicating downward motion. To distinguish vectors from points, the convention is to write this pair of numbers vertically with square brackets around them. Every pair of numbers gives you one and only one vector, and every vector is associated with one and only one pair of numbers. What about in 3 dimensions? Well, you add a third axis, called the z-axis, which is perpendicular to both the x and y axes, and in this case, each vector is associated with an ordered triplet of numbers. The first tells you how far to move along the x-axis, the second tells you how far to move parallel to the y-axis, and the third one tells you how far to then move parallel to this new z-axis. Every triplet of numbers gives you one unique vector in space, and every vector in space gives you exactly one triplet of numbers. Alright, so back to vector addition and multiplication by numbers. After all, every topic in linear algebra is going to center around these two operations. Luckily, each one's pretty straightforward to define. Let's say we have two vectors, one pointing up and a little to the right, and the other one pointing right and down a bit. To add these two vectors, move the second one so that its tail sits at the tip of the first one. Then, if you draw a new vector from the tail of the first one to where the tip of the second one now sits, that new vector is their sum. This definition of addition, by the way, is pretty much the only time in linear algebra where we let vectors stray away from the origin. Now, why is this a reasonable thing to do? Why this definition of addition and not some other one? Well, the way I like to think about it is that each vector represents a certain movement, a step with a certain distance and direction in space. If you take a step along the first vector, then take a step in the direction and distance described by the second vector, the overall effect is just the same as if you moved along the sum of those two vectors to start with. You could think about this as an extension of how we think about adding numbers on a number line. One way that we teach kids to think about this, say with 2 plus 5, is to think of moving 2 steps to the right, followed by another 5 steps to the right. The overall effect is the same as if you just took 7 steps to the right. In fact, let's see how vector addition looks numerically. The first vector here has coordinates 1, 2, and the second one has coordinates 3, -1. When you take the vector sum using this tip-to-tail method, you can think of a 4-step path from the origin to the tip of the second vector. Walk 1 to the right, then 2 up, then 3 to the right, then 1 down. Reorganizing these steps so that you first do all of the rightward motion, then do all the vertical motion, you can read it as saying, first move 1 plus 3 to the right, then move 2 minus 1 up. So the new vector has coordinates 1 plus 3 and 2 plus -1. In general, vector addition in this list of numbers conception looks like matching up their terms and adding each one together. The other fundamental vector operation is multiplication by a number. Now this is best understood just by looking at a few examples. If you take the number 2 and multiply it by a given vector, it means you stretch out that vector so that it's 2 times as long as when you started. If you multiply that vector by, say, 1/3, it means you squish it down so that it's 1/3 the original length. When you multiply it by a negative number, like negative 1.8, then the vector first gets flipped around, then stretched out by that factor of 1.8. This process of stretching or squishing or sometimes reversing the direction of a vector is called scaling. And whenever you catch a number, like 2 or 1/3 or negative 1.8, acting like this, scaling some vector, you call it a scalar. In fact, throughout linear algebra, one of the main things that numbers do is scale vectors, so it's common to use the word scalar pretty much interchangeably with the word number. Numerically, stretching out a vector by a factor of, say, 2, corresponds with multiplying each of its components by that factor, 2. So in the conception of vectors as lists of numbers, multiplying a given vector by a scalar means multiplying each one of those components by that scalar. You'll see in the following videos what I mean when I say that linear algebra topics tend to revolve around these two fundamental operations, vector addition and scalar multiplication. And I'll talk more in the last video about how and why the mathematician thinks only about these operations, independent and abstracted away from however you choose to represent vectors. In truth, it doesn't matter whether you think about vectors as fundamentally being arrows in space, like I'm suggesting you do, that happen to have a nice numerical representation, or fundamentally as lists of numbers that happen to have a nice geometric interpretation. The usefulness of linear algebra has less to do with either one of these views than it does with the ability to translate back and forth between them. It gives the data analyst a nice way to conceptualize many lists of numbers in a visual way, which can seriously clarify patterns in data and give a global view of what certain operations do. And on the flip side, it gives people like physicists and computer graphics programmers a language to describe space and the manipulation of space using numbers that can be crunched and run through a computer. When I do mathy animations, for example, I start by thinking about what's actually going on in space and then get the computer to represent things numerically, thereby figuring out where to place the pixels on the screen. And doing that usually relies on a lot of linear.
So I hope you got some intuition from that video on what vectors are, because I thought that his videos, three blue, one bronze videos, usually help any student to understand the intuition behind vectors. So where did we stop? So we stopped at this particular area, vector addition. Now, next operation that we're going to talk about is called this dot product or the inner product. So what is this dot product? If we were to read through it, it says besides addition and scalar multiplication, another important operation on vectors is the dot product, also known as the inner product. The dot product combines two vectors of the same dimension to produce a single number for vectors u and v. So we are taking, let's take u and v, a generalized set of vectors. U is given by u1, comma u2, comma up to un. Then another vector v, v1, comma v2, comma up to same number of components, vn. So what is this dot product? So the dot product u dot v is defined as you're going to multiply each component within each vector. So you're going to multiply u1 with v1. That's the first component in u dot v. The second component of u dot v is the two components here, u2 times v2, comma. Likewise, the final component is un, comma vn. You multiply un and vn, the last two components. So this would be your dot product, right? So the dot product is also important for us going forward. It's an important concept for you to learn. Now, I've taken an example here. I think that's also important. It's easier then. If you were to look at this particular example that I've given, we are going to take u as 2, comma 3, comma 1, and we're going to take v the other vector as 5 comma 1 comma 4. And then what do we do here? So we are supposed to calculate the dot product u dot v, which is the first product is 2 times 5, second product is 3 times 1, and the final product is 1 times 4. 1 times 4. Now, there is a mistake that I've done here. What is that? The u dot v is defined as you multiply and then you add. So here, the mistake that I made was I wrote it down as a vector. It is not. It is not a vector. You have to add all these terms, right? So when you add all these terms, the u dot v final output would be a number. So here we are adding all these terms. 2 times 5, 3 times 1, 1 times 4. So 2 times 5 is 10, plus 3 times 1 is 3, plus 1 times 4 is 4. And you see, you get a scalar or a number, which is 17. So small mistakes like this can happen. I think I mentioned this in the first lesson that I talked to you also. Now, this is very important. So a dot product or an inner product gives you a scalar. How does that happen? You're simply multiplying the components of each vector. That is, you had u1, u2, let's say u3, and v is v1, comma v2, comma v3. Now, u dot v, you know in your mind should give you a scalar, not a vector. So therefore, how do you get that? That is, you multiply the first two components plus you multiply the second two components plus you multiply the third component. So then this particular answer would be a scalar or or in other words, very simply put, a number, not not a vector, right? Okay, so that's a dot product. Let's skip over this particular interpretation. I don't think that's important. The interpretation over here, because this is a more mathematical interpretation, which I don't think is important for all of you. But the economic interpretation is important. So what are we saying here in terms of the economic interpretation? Um, So the dot product often represents a weighted sum. For instance, consider consumer purchasing n goods. So you have the quantity represented by Q and P represented by the price. So you have n products um, from 1 to n, and the total expenditure of the total expenditure of the consumer can be calculated using the dot product, right? So I've given an example here. So you're told Q is 4 comma 2 comma 1. We are looking at this particular example over here. Household consumes a bundle of goods 4 comma 2 comma 1. What is 4? 4 units of bread. 2 is 2 units of milk. And what is 1? 1 is 1 unit of um, egg. And what are the prices of each of these? Bread costs 2 units. Uh, and then milk costs 3 units and egg costs 0.5 units. So what is the total cost then? How do we calculate that? It's Q dot P, which is 4 times 2 plus 2 times 3 plus 1 times 0.5. That is 8 plus 6 plus 0.5. That is 14.5. 14.5 units. What is 14.5? That is the total cost spent by the household, by HH is household. So the dot product can be used if you know the quantity and if you know the price. You simply note down a quantity in terms of a row vector and prices of each of those quantities of the products that you're buying as a row vector in price. And then you simply take the dot product, which gives you the total cost spent by the household. So I've given a practice problem here. Why don't you take 5 minutes and try and do this particular practice problem? So it's 3:36, 3:37. Take about 5 minutes till 3:42 and try and do this particular practice problem. Okay, so the first question tells you interpret these vectors in economic terms. So you have the vector Q, which is the quantity of rice and the quantity of wheat. Simply, you have 100,000 tons of rice. You have 100,000 tons of rice and 50,000 tons of wheat. Why am I saying tons? Because look at how it's um, mentioned here. It says in thousands of tons. And then that's quantity. So price is simple. It's just lists the price per ton of rice and wheat in dollars. So basically, price is simply uh, per ton. Price is per ton of rice and wheat. So that's the interpretation of these vectors in economic terms. Then you're asked to calculate the country's total value of grain output by computing the dot product. So assume you're not told. Assume this part is not told by computing the dot product. Let's forget that. You asked calculate the country's total value of grain output. Total value. That's what they're asking. Total value. So that is Q dot P. So that is 200 uh, into what was Q? Sorry, this should be 100 into 200 plus 50 into 300. So 100 into 200 plus 50 into 300 would give you, this is 20,000 and this is 15,000. So that is 35,000. So what is this 35,000? So it's actually, if you look at the units properly, now the quantity is in thousands of tons. This is quantity. It's in thousands of tons. Um, so what we have here is not actually 100, it's 100,000. And what we have here is actually not 50, it's 50,000. So the final value we get here is 35 billion in total value. Right? So this is the value that the country gains from production. And then you have, if a new vector is q prime, so we are defining a vector here, q which prime, which is q plus 20 comma 10. What was q? Our q is 100 comma 50 plus 20 comma 10. So our new, this whatever this q prime is, a new one, it's 120. 100 plus 20 and 50 plus 10 is 60. So that's q prime. So what are they asking? What does the q prime represent? So q prime represents the output plan with 120 tons of rice and 60 tons of wheat. So there's an increase of 20,000 and 10,000 tons, respectively, for the from the original outputs. And what is the total value at the same prices? What is the total value at the same prices? So you take the dot product again. Um, that is 120 into 200 plus 60 into 300. So this would give you 42,000. And what is this? It's actually $42 billion in total value, because these numbers are in, the quantities are in thousands of tons. Um, so that's the example. What are some of the key takeaways from vectors? So vectors is an ordered list of numbers. That's the key thing that we looked at. So it can represent a point in space or a quantity in multiple dimensions. Vectors are added or subtracted component-wise, and multiplying by a scalar scales every component. I hope you remember in that particular video how he visually showed that to you. And then we talked about the dot product of two same-sized vectors yields a scalar. That's important. It yields a scalar computed by summing the products of the corresponding components. So that's an introduction to vectors. So from vectors, we go into matrices. From vectors, we go into matrices. So as you saw, vectors is a one-dimensional array of numbers, whereas matrices are a two-dimensional array of numbers. That's important to keep in mind. So for example, this is a matrix. So you've given A 251 4 3 7. Now this is called a 2 by 3 matrix. Why is that? There are two rows here. There's one and two rows and three columns. So these are your rows, row 1 and row 2. These are your columns, C1, C2, C3. So your matrix A is a 2 by 3, or you denote it as 2 multiplied by, this is not the multiplication, this is a denotion, 2 by 3 matrix. You don't say 2 times 3 is 6, no. This is just a denotion saying there are two rows and three columns. So any vector in general, you would write it as m comma n, where m is the number of rows and n is the number of columns, right? And each of these components, that is your 2 or 5, 1, 4, 3, 7, these are components within the matrix, and that is in general denoted by simple Aij, right? So when we take our example A, 2, 5, 1, 4, 3, 7, so this is a 2 by 3 matrix. It's called, each of these components are denoted by Aij. Why is that? So this first component, what is Inj? Aij. So what is Aij? Ij represents the row and the column. The row and the column. This gives you the positioning. So if you were to take this 2, that is A11. Why is that? 2 is in your first row and your first column, isn't it? So A11 is 2. How would you represent 5? So 5 is simple A. It's in your first row, okay, and it's in the second column, A12. How would you represent 3? So 3 is in your second row, second column, right? Fine. Let's say 7. 7 is in your um, second row, third column. So each of these components are represented by Aij. I is your ith row and J is the jth column positioning. So that's what we talk about here. So keep in mind, a matrix is, we consider it to be a two-dimensional array of numbers. Why is it two-dimensional? Now we looked at that. So a matrix is two-dimensional, 2D, because we have rows into columns, right? Whereas in a vector is one-dimensional because it's a row or a column. So in our example, A251437 is a 2 by 3 matrix. It's 2D because you have rows and columns. Whereas if you take, let's say, A1, only 251, let's say. So this is a vector. Why is that? Because it only has a row. Also, if you take A2, let's say 2, 4, this is also a vector. This is a column vector. This is a row vector. It's one dimensional. It only has a column or a row. Right. So now we are going to talk about types of matrices. There are different types of matrices. Um, so one such matrix type is this thing called square matrix. So in a square matrix, you have the same number of rows and columns. So we said matrix in general, A m by n, where N is the number of rows, n is the number of columns. So in a square matrix, you would have m equals to n. So for example, you can have a 2 by 2 matrix. Let's say 4, 3, 5, 7. Right? So 4, 3, 5, 7. This is a 2 by 2 matrix. Therefore, it's a square matrix. Let's take a 3 by 3 matrix. So that means that has 3 rows and 3 columns. 5, 8, 9, 10, 2, 1. So that's a 3 by 3 matrix. So it's a square matrix. Why? Because the number of rows and columns are the same. Um, then you have something called row and column vectors. So, which is what we looked at before, row and column vectors. But this is a special type of a matrix. Why is that? Because if you take a particular matrix, let's say A, 1 by n, what does this mean? This means this particular matrix has only one row, n number of columns. Let's say n is equal to 3. So then you would have A 1 by 3. So that would be uh, one row, 3 columns. So that is, let's say, 2, 5, 8. So it has one row. It has only one row, but here there are 3 columns. So what is this? This is a row vector. But let's take another one. B, let's take m by 1. So what is this? This is telling you there are m number of rows, but only one column. So let's take an example. Again, let's say 4 by 1. M is 4. So what's an example for this? So there are any number, right? So here you see there are 4 rows, row 1, row 2, row 3, and row 4, but only one column. So what is this? This is a column vector, right? So these are also, these row vectors and column vectors are also special types of matrices. So we first looked at what a square matrix is. Then we looked at what a row and column matrix, row and column vectors are, which is also a special type of a matrix. And then we come to identity matrix. What is this identity matrix? So it says the identity matrix IN is a special n by n square matrix. So first and foremost, the identity matrix is also a square matrix, but it has ones on the main diagonal. So this is an example of an identity matrix which is 3 by 3. So the identity matrix I3 is denoted by 1 0 0 0 1 0 0 0 1. So you see, an identity matrix has ones in its diagonal, the main diagonal, 0 elsewhere. Let's take I2, which is a 2 by 2 matrix, 1 0 0 1. Again in the main diagonal. Not, you can't, so this cannot be, this here is not, this is not identity matrix. Okay, so the ones have to be in the main diagonal. What we call here is off diagonal, right? So this is not an identity matrix. That's important to keep in mind. It's very important because you can easily make a mistake there. So this is not, sorry, this is not an identity matrix because your one is not in the main diagonal. Right. Um, so you remember the identity matrix is also a square matrix where you have ones in your main diagonal. So I4 is a 4 by 4 matrix. 0 1 0 0 0 0 1 0 0 0 0 1. So see, you have all these ones in the main diagonal. Everywhere else, it's 0. So the importance of the identity matrix is it acts like the number one under matrix multiplication, right? That's why it's key. So you take any identity matrix IN and you take any um, square matrix, let's say A n by n. So for example, let's take I3 and another matrix 3 by 3, right? So what they're saying here is IN times A equals to A, and A times IN is equals to A. So let's take an example. I3 is 1 0 0 0 1 0 and 0 0 1. Um, 3 by 3 matrix, let's say 2 3 1 4 1 1 1 3 4. What they're saying is, now we haven't learned matrix multiplication yet properly. What they're saying is when you multiply the identity matrix by your 3 by 3 matrix, you would get the 3 by 3 matrix as it is, and other way around. If you were to multiply 3 by 3 matrix by the identity matrix, you would still get the 3 by 3 matrix. Now, in real numbers, if you take um, real numbers, this is obvious, isn't it? So what we are saying here is it acts like the number one. So 1 times, let's say 3 is 3. 3 times 1 is also 3, right? In the real numbers. But matrices, this is not all in matrices. This is not always true. Not always true. Sometimes it is true. So one such occasion where it is true is this, where if you multiply a particular square matrix by its identity matrix having the similar number of rows and columns, um, you would get the same square matrix. And that's important to keep in mind. Then we move to, now we are talking about different types of matrices. Then we move to this thing called zero matrix. The zero matrix. So a zero matrix is again denoted by zero. Um, is where all entries are zero. It is the additive identity for matrices, meaning you add a zero matrix to any square matrix A, and you will get the same the same matrix A. Then you have the diagonal matrix. I've only covered some of the types of matrices, not all. There are other types of matrices also. So a diagonal matrix has all off diagonal entries as zero. Only the main diagonal have non-zero values. So this is an important one. This is where you can get a little confused. So a diagonal matrix, let's say um, uh, 3 by 3. So 2 0 0 0 5 0 0 0 6. Now this is a diagonal matrix. Why is that? Because all the main diagonal entries are non-zero and everything else is zero, right? But this is not an identity matrix. Why? Because in an identity matrix, this would be your main diagonal would always have the element component 1. This is an identity matrix. This is a diagonal matrix. So you have to know the difference between the two, where you can make a small mistake. Then we talk about this transpose of a matrix. So I think we talked about this in vectors as well, but transpose of a matrix. So a transpose of a matrix is similar to a vector, but remember vector is one-dimensional. A matrix is two-dimensional. So what is the example I've taken here? let's take this 3 by 2 matrix. Why is it 3 by 2? Because you have three columns and three rows and two columns. So A I have taken as 2, 5, 3, 4, 1, 0. Now, the transpose of matrix, you can have A prime or denoted by a T. How do we write that? You take the first column and you write it as the first row of your transpose matrix. You take the second column here and you write it down as the second row. So now you have the transpose of A, right? So this initially was a 3 by 2 matrix because there were three rows and two columns. When you transpose it, you have two rows and three columns. Now again, let's take another example. Um, let's take B as 1, 2, 3, 4, 6, 7, right? Now this is a 2 by 3 matrix. What is the transpose of B? The transpose of B is here I take the first column 1, 4 and put it as my row. The second column, put it as my second row. The third column, put it as my third row, such that this becomes a 3 by 2 matrix now. So the transpose of B is written like this. Now, in the case of you having um, a, a symmetric matrix, that's what I'm saying here. A special case is this, something called symmetric matrix. Um, a symmetric matrix is where the transpose and its original matrix is the same. So I've taken an example for a symmetric matrix. Symmetric matrix. So what have I taken? A is 1, 5, 5, 2. So the transpose of this would be, I take the first column and I write it as the first row, second column, write it as the second row, and you see, oh, A is equal to AT. So this A is a symmetric matrix. Why is that? Because A is equal to its own transpose. So I've said here, symmetric matrices often rises in economics. For instance, variance, covariance matrices in econometrics are symmetric by construction. So you will have your econometrics lesson, I think, in your second or third semester, and you will come across this variance, covariance matrices in under econometrics. So it's more of a technical aspect here. So it's important to understand. Now, I know there's a lot of technical things that we're talking about, um, but these are very simple. Just read through it two times because we're talking about types of matrices. And in calculations, you need to first quickly identify what type of a matrix are you dealing with. Is it a square matrix? Is it a row and vector column? Is it an identity matrix, a zero matrix? Uh, is it a diagonal matrix? What is the transpose of a matrix? Likewise. So similar to vectors, you have matrix operations in terms of matrix addition, scalar multiplication, and matrix multiplications. So let's take a look at matrix operations first in terms of matrix addition and subtraction. Very similar to vectors. Um, so let's take a matrix. For example, let's take A equals 2, 3, 1, 5, and you're taking another matrix B, 5, 7, 8, 9, right? So what do I want to calculate? I want to calculate A plus B. So what do? I add the corresponding components. What do I mean by that? I add 2 with 5. 2 plus 5 is my first component. The second component is 3 and 7. So I add 3, 7. Next, I add 1 and 8. 1 plus 8. Finally, I add 5 and 9. 5 plus 9. So then I get A plus B as 7, 10, 9, 14. Now, it may look simple, but there are some things that you have to keep in mind. Um, we have to make sure that the matrices that we are adding have a similar size. What do I mean by same or same dimensions? That's very key, provided they have the same dimensions. The same dimensions in the sense the same number of rows and the same number of columns. So for example, here I've taken a very simple example, a square matrix, which is 2 by 2 and 2 by 2. So then you can add, but let's also take another example. Um, so this is example number 1. Let's take another example, example number 2. Let's take A as 1, 2, 3, 4, 7, 9. So this is a 2 by 3 matrix. Let's take another matrix, which is 0, minus 1, 2, 5, minus 2, minus 3. This is also a 2 by 3 matrix. So I can add the 2. Why is that? Because I have the same dimensions. So A plus B would give me 1 plus 0 is my first element, 2 plus minus 1 is my second element, 3 plus 2 is my third element, and then 4 plus 5, 7 plus minus 2, 9 plus minus 3. So A plus B, I can add them because they have the same dimensions. I have 1 here. Then here I have 1, 3 plus 2 is 5, 4 plus 5 is 9, 7 minus 2 is 5, 9 minus 3 is 6. So A plus B. This is another matrix that I have, which is also 2 by 3, right? So I'm adding the components, each of these components, 1 with 0, 2 with minus 1, 3 with 2. That's what I have explained in detail in this particular area over here. Now in matrix addition, you have some properties, and I mentioned some of these properties. What is that? One is that matrix addition is commutative. That is, you add A and you add B to A, you would get the same answer as if you were to add A to B, right? So it's commutative. That's good to know. These two are the same. Remember, we are talking about matrices and not real numbers. And also, so what am I saying here? So we calculated A plus B in this particular example. Similarly, if you were to calculate B plus A in the same example, you should ideally get the same matrix, right? So that's what I'm saying here. A plus B and B plus A, it's commutative. That's one. That is one uh, property. The second property is it's associative. What do I mean by being associative? So if you were to add A plus B together and then add C, it is the same as saying you add the two B plus C together and then add A. So this is also the same. So this is called the associative law. It's called the associative property. That's what I mentioned over here. So these two properties you should also keep in mind when you're doing matrix additions and matrix subtractions. So I only did additions. Same thing applies when you're subtracting two matrices. Next up, we have scalar multiplication. Scalar multiplication. So in scalar multiplication, similar to vectors, what do we have here? So it says, just like with vectors, we can multiply a matrix by a scalar or a number by multiplying every entry of the matrix by that scalar. So you have a matrix, let's take 1, 4, 3, 0, and your scalar is, let's say, 2. So Ka, so you're multiplying the matrix by a scalar, would result in you multiplying each of these components 2 by 2 times 1, 2 times 4 is 8, 2 times 3 is 6, 2 times 0 is 0. You multiply all of the components by the scalar. That's what a scalar multiplication does. And in the scalar multiplication also, you have a particular property, which is it follows the distributive property. What do I mean by a distributive property? So if you were to add two matrices and multiply it by a scalar, it is the same thing as saying you multiply the particular matrix A by the scalar and you add um, the matrix B multiplied by the scalar. These two are the same. And this holds under usual distributive associative laws for scalar multiplication as well. Because this might seem very obvious to you if you have not studied matrices, thinking of real numbers. I keep telling you this because it's important. Um, these properties don't always hold, but in real numbers it does, but in matrices there are some areas where it does not. And we will come to that under matrix multiplication. But before we talk about matrix multiplication, let's take a 10-minute break and come back. So it's 4:12 now. We'll come back at 4:22. I would like you all to try these 4 exercises. So I've given 4 very simple exercises in matrices. The first one is matrix addition between 2 square matrices. Both are 2 by 2. The second one is matrix subtraction. Again, 2 by 2 matrices, square matrices. The third one is um, find the transpose of the given matrix. And that matrix is a 3 by 2 matrix. The fourth final one is a scalar multiplication of matrices. So just see whether you can do these two. So sorry, 4 exercises. So the first one is quite straightforward. A plus b, so you add 1 and 4, so you get 5. 2 and 3, which is also 5. 3 and 2, which is also 5. 4 and 1, so which is also 5. So A plus B is another 2 by 2 matrix, which gives you all 5s. And if you want, interestingly, you can take 5 out such that you have something like this. So it's a scale multiplication of the 1, 1, 1, 1, 2 by 2 matrix multiplied by 5. And the second one, A minus B, is 9 minus 5 is 9 minus 5 is 4. 10 minus 6 is 4. 11 minus 7 is also 4. And 12 minus 8 is also 4. So you can take 4 out such that you have something like this, a 2 by 2 matrix, where it's multiplied by a scalar 4. And then you have to find the transpose of A. So the transpose of A is also very simple. What is it? So you have the first column, you put it as a row. So the first column is 2, 4, 6. you write it down as a row 2, 4, 6. The second column is 3, 5, 7. You write it down as the second row. That's what you get. That's the transpose of A. And then you're simply asked to find the scalar multiple multiplied by 3. So that is 6 minus 3, 0. 3 times 4 is 12. These would be your answers. Very simple questions, just so that you get into writing. Right. Now we come across, so these are the answers. Now we come across something important, something called matrix multiplication. Matrix multiplication or matrix multiplication is not as intuitive as the previous ones, matrix addition or matrix scalar multiplication, because matrix multiplication works in a different way. So I thought before we come to that, it's good for you to have an understanding of what matrices are. So for that, we'll just watch
Squishes.
this 3 blue 1 browns video to understand what a matrix is doing intuitively, just like vectors. What happens in matrices, because we are going to use matrices for to solve linear equations in our problem set. So it's used as a linear transformation. So let's have a look at what matrices are.
Hey everyone! If I had to choose just one topic that makes all of the others in linear algebra start to click, and which too often goes unlearned the first time a student takes linear algebra, it would be this one: the idea of a linear transformation and its relation to matrices. For this video, I'm just going to focus on what these transformations look like in the case of two dimensions, and how they relate to the idea of matrix vector multiplication. In particular, I want to show you a way to think about matrix vector multiplication that doesn't rely on memorization. To start, let's just parse this term, linear transformation. Transformation is essentially a fancy word for function. It's something that takes in inputs and spits out an output for each one. Specifically, in the context of linear algebra, we like to think about transformations that take in some vector and spit out another vector. So why use the word transformation instead of function if they mean the same thing? Well, it's to be suggestive of a certain way to visualize this input-output relation. You see, a great way to understand functions of vectors is to use movement. If a transformation takes some input vector to some output vector, we imagine that input vector moving over to the output vector. Then to understand the transformation as a whole, we might imagine watching every possible input vector move over to its corresponding output vector. It gets really crowded to think about all of the vectors all at once, each one as an arrow. So, as I mentioned last video, a nice trick is to conceptualize each vector not as an arrow, but as a single point, the point where its tip sits. That way, to think about a transformation taking every possible input vector to some output vector, we watch every point in space moving to some other point. In the case of transformations in two dimensions, to get a better feel for the whole shape of the transformation, I like to do this with all of the points on an infinite grid. I also sometimes like to keep a copy of the grid in the background, just to help keep track of where everything ends up relative to where it starts. The effect for various transformations moving around all of the points in space is, you've got to admit, beautiful. It gives the feeling of squishing and morphing space itself. As you can imagine, though, arbitrary transformations can look pretty complicated. But luckily, linear algebra limits itself to a special type of transformation, ones that are easier to understand, called linear transformations. Visually speaking, a transformation is linear if it has two properties. All lines must remain lines without getting curved, and the origin must remain fixed in place. For example, this right here would not be a linear transformation, since the lines get all curvy. And this one right here, although it keeps the line straight, is not a linear transformation, because it moves the origin. This one here fixes the origin and it might look like it keeps lines straight, but that's just because I'm only showing the horizontal and vertical grid lines. When you see what it does to a diagonal line, it becomes clear that it's not at all linear, since it turns that line all curvy. In general, you should think of linear transformations as keeping grid lines parallel and evenly spaced. Some linear transformations are simple to think about, like rotations about the origin. Others are a little trickier to describe with words. So how do you think you could describe these transformations numerically? If you were, say, programming some animations to make a video teaching the topic, what formula do you give the computer so that if you give it the coordinates of a vector, it can give you the coordinates of where that vector lands? It turns out that you only need to record where the two basis vectors, I hat and j hat, each land, and everything else will follow from that. For example, consider the vector v with coordinates -1, 2, meaning that it equals -1 times I hat plus 2 times j hat. If we play some transformation and follow where all three of these vectors go, the property that grid lines remain parallel and evenly spaced has a really important consequence. The place where v lands will be -1 times the vector where I hat landed plus 2 times the vector where j hat landed. In other words, it started off as a certain linear combination of I hat and j hat, and it ends up as that same linear combination of where those two vectors landed. This means you can deduce where v must go based only on where I hat and j hat each land. This is why I like keeping a copy of the original grid in the background. For the transformation shown here, we can read off that I hat lands on the coordinates 1, -2, and j hat lands on the x-axis over at the coordinates 3, 0. This means that the vector represented by -1 I hat plus 2 times j hat ends up at -1 times the vector 1, -2 plus 2 times the vector 3, 0. Adding that all together, you can deduce that it has to land on the vector 5, 2. This is a good point to pause and ponder, because it's pretty important. Now, given that I'm actually showing you the full transformation, you could have just looked to see that v has the coordinates 5, 2. But the cool part here is that this gives us a technique to deduce where any vectors land so long as we have a record of where I hat and j hat each land, without needing to watch the transformation itself. Write the vector with more general coordinates, x and y, and it will land on x times the vector where I hat lands, 1, -2, plus y times the vector where j hat lands, 3, 0. Carrying out that sum, you see that it lands at 1x plus 3y, -2x plus 0y. I give you any vector, and you can tell me where that vector lands using this formula. What all of this is saying is that a two-dimensional linear transformation is completely described by just 4 numbers, the 2 coordinates for where I hat lands and the 2 coordinates for where j hat lands. Isn't that cool? It's common to package these coordinates into a 2x2 grid of numbers, called a 2x2 matrix, where you can interpret the columns as the 2 special vectors where I hat and j hat each land. If you're given a 2x2 matrix describing a linear transformation and some specific vector, and you want to know where that linear transformation takes that vector, you can take the coordinates of the vector, multiply them by the corresponding columns of the matrix, then add together what you get. This corresponds with the idea of adding the scaled versions of our new basis vectors. Let's see what this looks like in the most general case, where your matrix has entries A, B, C, D. And remember, this matrix is just a way of packaging the information needed to describe a linear transformation. Always remember to interpret that first column, AC, as the place where the first basis vector lands, and that second column, BD, as the place where the second basis vector lands. When we apply this transformation to some vector xy, what do you get? Well, it'll be x times AC plus y times BD. Putting this together, you get a vector AX plus BY, CX plus DY. You could even define this as matrix vector multiplication when you put the matrix on the left of the vector like it's a function. Then, you could make high schoolers memorize this without showing them the crucial part that makes it feel intuitive. But isn't it more fun to think about these columns as the transformed versions of your basis vectors, and to think about the result as the appropriate linear combination of those vectors? Let's practice describing a few linear transformations with matrices. For example, if we rotate all of space 90 degrees counterclockwise, then I hat lands on the coordinates 0, 1, and j hat lands on the coordinates -1, 0. So the matrix we end up with has columns 0, 1, -1, 0. To figure out what happens to any vector after a 90-degree rotation, you could just multiply its coordinates by this matrix. Here's a fun transformation with a special name, called a shear. In it, I hat remains fixed, so the first column of the matrix is 1, 0. But j hat moves over to the coordinates 1, 1, which become the second column of the matrix. And at the risk of being redundant here, figuring out how a shear transforms a given vector comes down to multiplying this matrix by that vector. Let's say we want to go the other way around, starting with a matrix, say with columns 1, 2, and 3, 1, and we want to deduce what its transformation looks like. Pause and take a moment to see if you can imagine it. One way to do this is to first move I hat to 1, 2, then move j hat to 3, 1, always moving the rest of space in such a way that keeps grid lines parallel and evenly spaced. If the vectors that I hat and j hat land on are linearly dependent, which, if you recall from last video, means that one is a scaled version of the other, it means that the linear transformation squishes all of 2D space onto the line where those two vectors sit, also known as the one-dimensional span of those two linearly dependent vectors. To sum up, linear transformations are a way to move around space such that grid lines remain parallel and evenly spaced, and such that the origin remains fixed. Delightfully, these transformations can be described using only a handful of numbers, the coordinates of where each basis vector lands. Matrices give us a language to describe these transformations, where the columns represent those coordinates, and matrix vector multiplication is just a way to compute what that transformation does to a given vector. The important takeaway here is that every time you see a matrix, you can interpret it as a certain transformation of space. Once you really digest this idea, you're in a great position to understand linear algebra deeply. Almost all of the topics coming up, from matrix multiplication to determinants, change of basis, eigenvalues, all of these will become easier to understand once you start thinking about matrices as transformations of space. Most immediately, in the next video, I'll be talking about multiplying two matrices together. See you then.
So that's what we are going to look at. So I wanted you all to watch that video because he very nicely explains the intuition behind what happens in a matrix and what it does. It linearly transforms the grid that we are in. But of course, you don't need to know that, but it's good to have an intuitive idea of what what matrices does. But coming back to matrix multiplication, so in matrix multiplication, um, how we do it is what I'm going to explain to you. So it's best explained through this particular example that I've taken over here. So let's take this example. So you have A, which is a 2 by 3 matrix, 1, 2, 3, 0, -1, 4. And then you have another matrix B, which is a 3 by 2 matrix, 2, 1, 3, 0. This is 2 by 3. Then 1, 5. This is 3 by 2. Now, first and foremost, for these two matrices, to be multiplied, there's an important condition. What is that? The matrices can only be multiplied when the number of columns of your first matrix is the same as the number of columns in your number of rows in your second matrix. So basically, in this case, the example that I've taken, the number of columns is 3 in your first matrix because you're multiplying A times B, and the number of rows in your second matrix are the same. So these two are the same. So that needs to happen for you to calculate the multiplication of these two matrices. That's the first thing you have to check. The number of columns in the first matrix and the number of rows in the second matrix should be the same. So then how do we go about calculating? Well, That's what I have explained here in detail. How do you calculate each component? And what is the resulting matrix like? So the resulting matrix C would be a 2 by 2 matrix. Now, how did I get this? It is because you have two rows, and two columns. Two rows in your first matrix, two columns in your second matrix. So because of that, your resulting matrix would be a 2 by 2 matrix. Now, how do you calculate C? So it's a 2 by 2 matrix. How do you calculate? So you have different components. You have C11, C12, C21, and C22. What is this? These are the components. Um, so how do you calculate C11, the first component? So the first component you calculate, um, you take the first row, 1, 2, 3, and then you multiply, that is 1, 2, 3, this particular row, and then you multiply it by the first column. And then you add each component. So what do I mean by that? So you take 1 times 2 plus 2 times 3 plus 3 times 1. 1 times 2. So let me put it in another color so that it's clear for you. 1 multiplied by 2. And then plus 2 multiplied by 3 plus 3 multiplied by 1. So what is the answer that we get then? So here you would get 1 times 2 is 2, 2 times 3 is 6, plus 2 is 8, plus 3 is 11. So here, so something that I missed out. Yeah, sorry, I missed out here. So it's actually negative 1. So it's negative 1 here. That's what I was wondering. So it's negative 1. So then 2 plus 6 is 8, minus 3 is 5. That's your first component, C11. C12, how do you calculate that? Then you take the first row and then you multiply it by the second column. So you take the first row and you multiply it by the second column. So you have the two matrices here. You take the first row, multiplied by the second column to get C11, C12. So that is 1 times 1 plus 2 times 0 plus 3 times 5. And that gives you 16. This is a little bit tricky. So you need to practice a lot on this. So how do you calculate C21? Sorry, C21, this component. So that you calculate, you take the second row and you multiply it by the first column. You take the second row and you multiply it by the second column. Second row multiplied by the first column. So then you have 0 times 2 plus minus 1 times 3 plus 4 times minus 1. So then you get um, minus 7. And then similarly, C22 is, what do you do there in C22? Sorry. In C22, you take the second row and you multiply it by the second column. That's what you do. So your second row is 0, first component 0 times 1 plus minus 1 times 0 plus 4 times 5, and that gives you 20. So now your C, which was A times B, the two matrices multiplied. The first component is 5, C12, C11, C12 is 16, C21 is minus 7, C22 is 20. So how we do it in detail, I have explained over here. So I think that's important that you go through it. So just one more time, if I were to run through this, I'm multiplying two matrices, A and B. So A and B, what is the condition that allows me to multiply? The condition is that the number of columns in the first matrix, number of columns in the first matrix should be the same as the number of rows in the second matrix. That's the first condition, right? Then you know you can multiply the two matrices. Then in multiplying the two matrices, that is A times B, which is C, which is a 2 by 2 matrix. How do you go about doing that? Well, C is a 2 by 2 matrix, which means it has four components: C11, C12, C21, because it's second row, first column, and C22, second row, second column. So how do you calculate C11? C11 means is you take the first row of A and you multiply it by first column of B component wise. So you take the first row of A, what is that? 1, 2, 3, 1, 2, 3, and you multiply it by the first column of B. So that gives you 1 times 2 plus 2 times 3. So it's basically the dot product, 3 times minus 1. And then you get 5. Similarly, if you were to look at C12, you would take the first row of A and the second column of B, which is 105. 105. So you take the dot product again, 1 times 1 plus 2 times 0 plus 3 times um, 5. So that gives you 16, right? So that's what we got here, 16, 5, minus 7, and 20. So that is matrix multiplication. Let me just try and... Right, so that is matrix multiplication. Um, in matrix multiplication, let's have another look at another example, because you need to do a lot of examples. Let's take example A and 1, 0, 2, 3, and then B. So these are 2 by 2 matrix. B is 4, 5, 6, 7. So it's also 2 by 2 matrix. So you know that the number of columns in A and number of rows in B are same. So you can calculate A times B. Let's take it as a matrix C, which has to be a 2 by 2 matrix, which is C11, C12, C21, C22, right? So how do we calculate C11? C11 is you take the first row of A multiplied by the first column of B. So that is 1 times 4 plus 0 times 6, which is 4. C12 is you take the first row of A, 1, 0, multiplied by the second column of B, 5, 7. So you get 1 times 5 plus 0 times 7, which is 5. C21. So now you take the second row of A multiplied by the first column of B. 2 times 4 plus 3 times 6. So 2 times 4 is 8, 3 times 6 is 18, 18 and 8 is 26. And then finally C22 is you take the second row of A and you multiply it by the second column of B. 2 times 5 plus 3 times 7, 10 plus 21 is 31. So therefore, your matrix C, which is A times B, is 4, 5, 26, 31. Now, what's interesting is in matrix multiplication, A times B does not always equal to B times A. There are only special occasions where these two are equal, but not in all occasions. So if you were to calculate B times A here, in our example, what would we get? So let's write down the matrices again because it's easier. B was 4, 5, 6, 7. A is 1, 0, 2, 3. So we are asked to calculate B multiplied by A. So that is, I'm going to write it down directly. First row, first column. That is um, 4 times 1 plus 5 times 2. That's the first component. Second component is first row, second column, 4 times 0 plus 5 times 3. Um, the other component here is the second row, first column. So that is 6 times 1 plus 7 times 2. Then second row, second column, 6 times 0 plus 7 times 3. So you get 4 plus, so you have 14 here, 4 plus 10. You have 15 here. You have 6 plus 14, which is 20, and 21. So you see, this is B times A. So you see here that A times B, which you got 4, 5, 26, 31, this one, and B times A is 2. 1 and 2 are not the same, right? So that's normal. I mean, in matrix multiplication, it's not commutative at all occasions, but it is associative. And that's what I have mentioned here. It is associative, and the distribution over addition also applies here. So we learned a lot today. I think we should wrap up today because it's a little too much if not. So what I want you to do is I will send you a problem set and I will send you this lecture. Go through vectors, vector addition, vector subtraction, vector multiplication, vector scalar multiplication of vectors, and also different types of matrices that we talked about, and then matrix operations up to matrix multiplication. Um, Go through it, practice matrix multiplication a lot because that's the tricky part. And the intuition behind it is what you got from that particular video that we watched. So from matrix multiplication, we go into matrix vector multiplication, which is what that video told us about, which is of this linear transformation, how you linearly transform a vector's position by multiplying it by a particular matrix. And then we talk about the economic examples of vector matrix multiplications. Um, we will go through these in the next lesson, and then we come into linear equations. That is solving linear equations using matrices. That's what we are going to do, in which we are going to talk about the determinant of a matrix, inverse of a matrix, all these components. But for all of this, you need to practice a little bit on matrix multiplication and other aspects, the other segments that we covered today. If you have any questions, please do ask. I will remain, but if not, that's it for today's lesson. Remember, 5th July is when we set the mid-semester exam. I have sent already. I have sent you 2 emails, one the original and a reminder with a practice set of problems. Please go through those practice set of problems because the solutions are also there, and I've sent a commentary separately. So that would be helpful for you to face the mid-sem exam. In the mid-semester exam, we will also have matrices covered as well. There will be one problem from matrices. So that's it for today. Thank you very much. I will hang around for about 5-10 minutes if you have any questions. Thank you.